are ready. Could you talk through what you've built?
Sure. So yeah, we built a mini golf game, sort of a golf simulator-esque game where we have a real putter. This is from when I played high school golf. This is the putter that I use, so it's pretty old. And yeah, we put a 9-axis IMU on it, and we're really only using the accelerometer and the magnetometer. The accelerometer to detect differences in acceleration, obviously, when we're swinging the club, when we bring it back and bring it forward. And the magnetometer we're using to get heading. We have this styrofoam mat on the ground, and we put these two little strong magnets. We weld them inside, and you can tell we've tested two different distances, one where they're closer to the club head and one where they're further away. And based off the magnetic field and the different readings, you can see up here, when I move the club, it moves the...
How cool.
It moves that. So thanks to Bruce for that great idea.
So these overwhelm Earth's magnetic field, so you get a really
very
strong magnetometer reading.
But the problem with them too close to the middle was that they overwhelmed the magnetometer. So, for example, if you can see, when it gets too close to it, it just kind of goes nuts.
Oh, neat, yeah.
So when they were in the middle, it kind of just went nuts a lot, especially since we're moving the club head back and forth, and it often it got too close to the magnets.
Yeah.
So yeah, we have a couple of different holes, and varying sort of shapes.
Okay.
And I can sort of show you how we play.
Sure.
And since with these magnets and the orientation, you can really only measure 180 degrees. So we have this feature on the keypad that by pressing the number 9 key at any time you can rotate by 90 degrees.
Okay.
So it goes 90 and then back flips around.
So that's your sort of very coarse alignment, and then you do your fine tuning.
Yeah, exactly.
Gotcha. Okay.
So how we sort of detect the swing elements is first we look for a backswing, which is we get negative acceleration, which is when we sort of detect the beginning of a backswing. And then at 0, when sort of your momentum shifts from back to front, that's sort of when we start the front swing. So we also, at the beginning of the backswing, collect a bunch of these heading datas.
Okay.
And we will lock in on sort of the average of like what they were between like 20 samples or so. So when I swing, they'll detect the backswing, and then the ball.
Oh,
moves.
cool.
It is a little sensitive, so we've got 2 swings on that.
Okay.
But I'll see if I can put it in the hole if I retain any of my golf skills from high school. I still do play, but oh, it didn't. Okay. Oh, go. Yes. Okay.
Very
So
nice.
when it goes, it updates the hole to this new one.
Okay.
And you saw on hole number 1, it was a par 3, and I got it in 3. So
Yeah.
my score is still even. Or on hole number 2. We call this a par number 5, and I'm at zero strokes so far. So if I try to pound this thing up.
When it collides off the wall.
So we've had some difficulties with the bouncing. I don't know, Bobby, do you want to get into the bounce?
Yeah, on occasion, the ball will phase through the boundary outside of the green.
Okay.
It seems to a lot of the time happen when it's hitting a corner, but also sometimes even when it's not hitting a corner.
Okay.
So we can't even really replicate that.
Okay. Cool.
But it's supposed to detect collisions just by we wrote a function called read VGA, which sort of does draw a pixel in reverse. So we can sense when there's a white pixel around the ball, and then we have a normal vector associated with each side of the green. So then we use that to change the direction of the ball.
Very nice.
And then another, I think, neat thing that we did that we also ran into issues with was actually generating the holes. Do you want to talk about that too? Because it was a cool implementation.
Yeah. So we wanted to make it easy to create many holes to different shapes, and when you create each hole, you need to draw the boundary and draw the inside green. So we wrote a C function or file that does that. Where you can just input a set of vertices, and it will generate a new image of the new polygon.
Cool.
You basically put the vertices in clockwise order.
And it does obviously concave polygon.
Yes, it does.
That's not easy.
But there were several shapes that we tried where it did not look like this. There were sections of green outside the green, sections of black inside the green.
Okay.
And so we basically had to not use those shapes, basically. And we could not figure out what would make a shape work or not.
Sure.
Simpler shapes seem to work.
Yeah.
And it's clearly picking up not just that you have made a putt, but also something about the velocity of the putt.
Yeah, so we sort of equate acceleration to speed in this sense, even though that's
Just the acceleration from
the front swing.
when you start the front swing to when you reach your maximum speed.
Okay.
Because obviously the swings with higher acceleration will yield a higher ball speed. And since we're really only operating on like the X axis, and when you're putting, you're trying to be as flat as possible. So unlike sort of our lap 3 where we had like the circular rotation where we're sort of able to get the like complementary angle between two different axes, this is really just on a line.
Yeah.
So we couldn't really do that. So it does make sense to sort of like equate higher accelerations to higher velocities, just because like obviously when you're playing golf and you're trying to get one up a hill, for example, you're going to put some more acceleration, more speed into your club. So that's sort of what we're trying to get here.
Very nice. The magnetometer based orientation with the magnet seems to work really
works
nicely.
Phenomenally. Except we sort of thought that we would be able to get like 360 degrees, like if I would be able to like spin like around and whatnot.
But you still want to be sort of facing the
But
screen.
you do still want to be facing the screen, so we did like this idea of being able to like move the pointer vector and then be able to like.
And it kind of makes sense. It's almost like you're using that phaser.
Oh, there we go.
There you go. Well,
It's almost like you're using that to
demonstrate
like
a reset button now.
set your feet up or something, and then doing the fine adjustments as you would with a real putt.
And
Reset button.
interestingly, the calibration of orientation of the putter to the heading angle as it appears varies based on the location that the system is. We spent last night across the hall, and we found it was different, like at height table level versus at floor level. And then when we moved over here, we had to recalibrate it again by changing some parameters.
Wow.
So it's sensitive to the larger environment.
Mm-hmm.
Oh, it's because of the rebar in the floor.
The what?
Rebar in the floor. These are steel reinforced concrete floors.
That makes sense, actually. Yeah. That makes perfect sense.
Really nice, guys. Really nice.
It probably also changes calibration if you rotate that just
Yeah.
And I mean, so I first tested it in my apartment where I don't think I have rebarred floors in my old Ithaca house
Yeah, I
that was
don't think
probably
so.
built in like the early 1900s.
You're in one of the old mansions or whatever it is.
It's not a mansion, but it's a house split up into many apartments.
That's wood.
Yeah.
Yeah, it's all wood probably,
Yeah.
and it was completely different measurements to this and similar-ish magnet distance. So.
Very nice.
And then we're using I2C, we've talked about, to communicate between the magnetometer and IMU and the Raspberry Pi. And one thing that was extremely frustrating was getting this set up because there's two different I2C devices on this chip. The 6-axis IMU, which has the accelerometer and gyroscope, and then there's a separate magnetometer device, and you have to basically tell the 6-axis IMU to read the values of the magnetometer and put them into its own registers so that you can just read concurrent registers.
Oh boy. Okay.
So that took a while just in terms of looking at how other people were doing that and seeing that there were some differences and playing around with the differences until it finally worked.
Okay.
But it had to do with like enabling the master mode on this and telling it like to
Sure.
read from the register. And it's an interesting block diagram because you can see too that the there's a separate I2C interface, but then they're like connected to each other
Okay.
in a way. So that was a pain for
That's a lot of work.
a little bit,
Yeah,
but
yeah.
we got it going so that the IMU is reading from the magnetometer, so that we just have to read from like however many concurrent registers in a row, so you don't have to jump around.
I see. So the alternative would have been you would have had to switch between two different devices.
Yeah. And there is another interface on it, but that would have also taken a while to get that going.
Did you have any trouble with the meter-long wires?
So yes and no. The no answer is like they worked, it was fine. And I don't know if this is because there were meter-long wires or not, but then we slowed down the baud rate of the I2C.
We were observing some freezing.
Yeah,
Okay.
Which what was probably due to some.
Yeah.
And dropping the baud rate helped.
and it made everything look snappier on here, which
Great.
presume
Yeah. Yeah.
is easier on the Raspberry Pi anyway.
Because the default baud rate's pretty darn fast. If I
yeah, it
remember.
was like 400K.
Yeah.
We took off a zero.
We took off a zero. Yeah.
Okay.
40K.
Yeah.
Wow.
Yeah, that significantly helped.
Good.
I was like, might as well start dramatic and see
Yeah.
where we need to go, and it worked.
Really nice. That's a really, really cool project.
Thank you.
Awesome, guys. Thank you.
It's been fun
Yeah.
to do it. Yeah.
This is one of those